Betacam was developed to give full film-style mobility to ENG crews and to give picture and sound quality subjectively comparable to 1 inch. Every part of the Betacam system has been designed to interface with existing equipment and to be capable of future expansion.
That was what we said 4 years ago, and the same is true today, now that Betacam boasts SP performance, AFM and PCM sound, library management systems, digital interfacing, and many more improvements, with the promise of fully digital machines to come. Tape is at the very heart of Betacam, so it's natural that we should start by looking at the type of tape used. It is 1/2 inch wide, can be of metal or oxide formulation, and comes in all durations, from 5 to 90 minutes. Even portable machines can take large cassettes. The tape timings actually refer to 60 Hz based systems. In fact, with 50 Hz machines, that 10 Hz difference gives 20% more running time. So marked 30 minutes will run for 36. Before we can look into the practical aspects of Betacam, we must start by defining what we mean by component recording. This diagram shows that a component signal has separate luminance and chrominance, comprising Y, R-Y and B-Y in baseband form. These remain effectively separate all the way through the system, even at the record heads. Of course, analog recording methods still need conventional FM modulation to put the signal onto the tape. It may be useful at this stage to look at an example showing a confusing use of the term component. Colour-under systems using S connectors are incorrectly referred to as component. They are basically Y and C separated, but the C is down-converted and combined as a colour-under signal in a single head for recording, so it really cannot be looked upon as a component recording system. Betacam falls into the true component category, keeping the Y and C signals apart, and only combining the R-Y and B-Y in baseband form. This is done by time compressing the signal. This is called CTDM, short for compressed time division multiplexing. The only modulation which needs to take place is the normal FM modulation required by the tape characteristic. It is interesting that although the heads are part of the same block, they will have different time base errors. Therefore it is necessary to have separate sync references on the tape for Y and C, so that they may be correctly timed relative to one another to give a coherent playback image. In the Y channel, the conventional sync pulse is replaced by a tri-level sync. This has the advantage over conventional sync as it has 0 APL. This means that each time the signal is AC coupled, there is no bounce, as the average picture level of the sync is 0. This larger sync edge will also have a better signal-to-noise characteristic. The chroma signal tends to be symmetrical about blanking level, so this large, narrow 2 microsecond sync is added. Here are graphs showing the frequency allocation for conventional Betacam and for SP. As we can see, the frequencies have been increased, giving more headroom for the harmonics. The increase in frequency also reduces any moire component. In the chroma channel, 2 AFM carriers can now be installed here at 310 and 540 kHz. They form audio channels 3 and 4. Of course, other improvements, such as an increase in chroma bandwidth from 1.5 to 2 MHz, have accompanied this increase in frequency, thereby enhancing the overall performance of SP machines. The tape path too has changed over the years, and now favours different threading methods, with many small changes in the design. Note that this later design enables the cassettes to move further in, taking advantage of the cassette shape, making the tape path even more compact. Meaning the amount of tape wrapped around the drum has also changed. Here we can see two of the most common tape paths. The tape comes off the supply reel, past the full arrays head, and for portable machines it's placed here for better use of space. A tape tension regulator helps to control the back tension around the head drum. The control track head is responsible for making sure the tape is in the correct position. It does this by laying down a 25 Hz reference signal onto the tape. These are the entrance and exit guides, which are essential to maintain accurate tracking of the tape around the head drum. The audio and timecode heads are positioned here, next to the pinch roller and capstan. They are responsible for moving the tape at the correct speed, coupled to a stable reference. The rest of the tape path is made up of guides, and finally the tape goes onto the take-up reel. In PCM machines, the wrap is extended by approximately 8 degrees by this movable guide. This enables the sound to be recorded by the video heads, forming PCM segments in place of the Audio 1 longitudinal track. Looking at a head drum capable of PCM sound, we can see some additional heads. These are for pre-reading the PCM, to give an advance of 2 fields. This allows for the delay taken to process the PCM audio. You may have noticed that this head drum, which is used for camcorders, is smaller. The wrap angle is 270 degrees and uses 4 heads instead of the usual 2, but it maintains the same tape format. To do this, the drum speed is increased by 50%, from the standard 25 revolutions per second to 37.5. This means absolute compatibility with machines that have the larger size of drum. The head drum itself requires further explanation. Here is a BBW75P drum removed from the machine. Here are the record playback heads, the arrays and dynamic tracking heads. The luminance head is 86 microns and the chroma head 73. Remember, it is this dimension that causes the track width. The dynamic tracking head, or DT for short, can move vertically so as to follow tracks at different tape speeds. Looking more closely at the arrays head, we can see it is about twice the height of the RP heads, because it erases both Y and C tracks at the same time. The head labelled Erase A is placed so that it cannot erase the adjacent chrominance track. We can therefore say Erase A leads head A by 240 degrees. Looking more closely at the RP heads shows that they are stepped by 4 mm like this. So they line up on the tracks 12 horizontal lines apart. That means that when the Y head is on line 1, the C head is also on line 1 of its track. But remember, due to the compression process, there is 1 line delay in the chroma channel going onto the tape. It will be compensated for on the replay side of the machine. Here we can see the head azimuths. They are each set at 15 degrees, giving a relative 30 degrees when combined. making any adjacent track equivalent to a guard band. Here is a block diagram showing the record path. And although Betacam is a component system, machines do include composite decoders and encoders. Therefore we will start from a composite input and go through to a composite output, explaining all the other interface possibilities along the way. The composite signal must first be decoded into Y and C. This can be done with simple filtering techniques or using differing degrees of combing and correlation. The ultimate way is digital decoding, using both spatial and temporal sampling. All these methods are available within Betacam. As part of the decoding process, the SCH phase of the incoming signal is measured, and two extra signals formed. These help to lock the servos and improve the composite recoding process. The first of the two signals are colour identification flags, which are gated into the B-Y vertical interval on lines 12 and 325. The first positive going pulse of the group gives the start of the 8-field sequence. As the flags are essentially either 0 or 180 degrees, they cannot portray any error in the SCH phase of the incoming signal. It is the second signal which does this. It is called VISC, short for Vertical Interval Subcarrier. It captures the incoming signal's subcarrier in the form of a pilot burst and puts this into the vertical interval of the Y signal on lines 8 and 321. However, to accommodate the lower bandwidth Voxide tapes, the subcarrier frequency is divided by 2 in PAL machines. The chroma is demodulated into R-Y and B-Y, and should now be time coincident with the Y signal. The waveform looks like this. And it is this signal that we refer to as component. It is at this point in the chain that the interfacing to other component devices takes place. We now continue our block diagram at the point where a component signal enters the system. The chroma is now compressed. The compression process takes one horizontal line to process the signals. It happens like this. During a normal line period, the R-Y and B-Y signals are stored. And then during the next line period, clocked out in turn at twice the input rate. The R-Y being first. Finally, Betacam style sinks are added to the signals. There are two compression systems in use, one using CCD delay lines, and the other a process of analog to digital conversion, coupled to a digital memory and conversion back to analog. Next in the chain comes nonlinear preemphasis, normal FM preemphasis, and a balanced modulator to convert the signal to the RF domain. The RF is then amplitude modulated. But why? Because when there is a high frequency edge, some sidebands will be too low a level causing undersaturation of the tape, which could cause bearding, which looks like this. Some machines include a slew rate limiter to stop overmodulation. Here, the chroma channel will have a notch filter to clear a space at the bottom end of the frequency spectrum so that AFM sound may be inserted. The signal then passes to preamplifiers and through to the rotary transformers and onto the heads. The playback side has a few alternatives, based on whether a time-based corrector is used. We will be taking the simplest option first. This shows the block diagram of the playback electronics without TBC. There is the usual RF switching, demodulation and equalization. The signal at this point is CTDM and could be used for dubbing to another machine. This signal will of course be jittering with time-base error, but when it is expanded to component, it must have perfect YC timing. This means that both Y and C will jitter in perfect time together. This is done by looking at the demodulated playback sync of both Y and C and comparing their relative phase. A CCD delay line is placed in one channel and clocked with a VCO using the YC error to vary its electronic length. This reduces any timing offset between the two signals to 0. The component output is formed by expanding the chroma in the reverse manner to that of the compression. In some models, the chroma is combed and correlated to reduce line-by-line errors. As this is essentially an averaging process, the signal-to-noise of large colour areas will be improved by some 3 dB. The expansion process takes one line period, so the chroma channel is now up to 3H delayed with respect to the luminance. 1H used by compression, expansion and YC timing respectively. This can be compensated by putting a 3H CCD delay in the Y channel. Or, if dedicated playback heads are used, the spacing of the Y and C heads can be reduced from 12H to 9, creating a mechanical advance of 3 lines. We will now consider the TBC playback option. Why do we need a TBC? The last playback circuit let us play back on a monitor, hopefully with fast AFC, and dub to other machines, with jitter of course. But we couldn't use the output for any application which essentially involves stable timing, such as mixing. To do this, we need a TBC. We can think of it as water coming out of a tap in spurts and falling into a tank. If the tank is empty, there'd be no change in the flow, as it would go straight through. But as soon as the reservoir is formed in the tank, a steady flow would happen. In a TBC, the reservoir is a solid-state memory. This delay gives us time to process the incoming signal. With a device like a TBC, which uses electronic delay to perform its correction, there's a need to create an advance in time. This is so we can cope with both early and late timing errors, and have sufficient headroom in both directions. This is not impossible, as video is a repetitive system. A typical TBC has 32 lines of delay. And to create our pseudo-advance, the halfway point of the memory is designated as zero output time. To achieve this, the drum timing is advanced by 16 lines. Now that we've looked at the basics of time-based correction, let's look at its application within Betacam. We have already said that Y and C have different output timings due to the spacing of the heads, that 2 TBCs are required. So here is a block diagram of a dual TBC. Y and compressed C have their respective sinks accurately separated to reflect precisely any off-tape timing errors. This is due to a number of reasons. The first is mechanical errors, which are normally greater than 10 milliseconds. Electromechanical skew and tension errors are typically from 1 microsecond to 10 milliseconds. Velocity errors are from 10 nanoseconds to 1 microsecond, whilst phase errors are less than 10 nanoseconds. The signals are then clamped and converted to digital form. Any all 0 bytes are incremented to 1. These all 0 bytes being reserved for dropout identification in the memory. Video data is written into the memory using write clocks, timed to the playback sinks. Starting with a write 0 pulse, a fixed number of samples are clocked in, 864 in the case of machines capable of digital output. A fixed number of samples per line makes design straightforward. But what happens if the line length changes? Which of course happens. Well, it's easy. If the line length is longer, the samples are spaced further apart, and if it is shorter, they'll be closer together. This is achieved by making the write clock frequency track with line length. On the read side, dropout correction is performed together with the expansion of the chroma signal back into R-Y and B-Y. Several digital noise reduction techniques are used. These reduce noise on edges and large area color. The output of the TBC is of course a component signal. If required, the TBC output can be encoded for composite environments. You may be interested to know that both Sony and Dolby noise reduction techniques are covered by another tape in this series.